important to get that big picture down. So don't lose track of that big picture overview that we went through last time. But now we're going to start getting into the nitty-gritty, right? So we need to introduce a new topic here. Some of you have seen it before, but we need a new object in mathematics to start talking about this idea of something approaching something else, getting closer and closer to something else. We're actually going to just give, here I said, a not precise definition of the limit. Okay, so we will give the precise definition of the limit in section 2.7, but I'm actually going to even postpone that until after the first test because that definition is a very complicated definition, and this definition is good enough for what we want to say. So suppose we've got a function f that's defined on some open interval containing the point x equals a. It may not be defined at a itself, but it's defined around a at least. Okay? Then we say that the limit as x approaches a of f of x is equal to some number L if the following holds. So if the values of f of x become arbitrarily close to the number L, as the values of x become arbitrarily close to the value a. Okay. This is a complicated definition, folks. There's a lot going on here. Okay. First of all, something I think that will be extremely helpful is to always be paying attention to what are domain values and what are range values. Okay. What is this saying? This is saying the limit as x approaches a. That is, the limit as the domain values get closer and closer to a for the given function f of x will be L. Okay, what is L? What type of object? All right, take a second, just read through here.
A line.
Not necessarily a line.
A limit?
No. Well, we will call it the limit.
Function?
It's not necessarily a function.
The slope?
No.
It's a value, like a range.
So it's a value in the that the range values are getting closer and closer to. Okay. So the picture looks something like this. Okay. So let's say we've got a function that's behaving, I don't know, something like this right here, and we've got some value a that we want to talk about. Okay. I want to describe what the y values are doing as the x values get closer and closer to a. Okay. So I'm going to be taking x values on either side of a. How can I do that? Because f is defined around a. So I'm going to take values on either side of a, and I'm going to bring them closer and closer to the domain value, to the value a, the point a. It may not be in the domain of the function, but it'll be, these x values are going to get closer and closer to a. And what we want to decide then is, are the y values, as I do that, getting closer and closer to some number L? So for example, if I look at this point right here, when x is, see this first arrow that I drew? When x is this first arrow here, that's the corresponding point on the graph, right? Which has this corresponding f of x value, right? Then if I take another x value that's even closer to a, that gives me this new f of x value, right? And as I get even closer, it seems to me that as I do that, the y values are getting closer and closer to some number L. Okay? This is kind of a messy diagram. We're going to get a better instance of looking at it here. Okay? So what I want to make sure, though, is that we can all read math, right? So one thing you need to make sure you can do is just literally translate the symbols into a word sentence. So I'd like everyone to, we're going to read this together. This is, I mean, math's a foreign language, right? So we're going to practice saying the foreign language out loud. This says the limit as x approaches a of f of x is L. Okay, all together? The limit as x approaches a of f of x is L. You guys are horrible. Let's try that again. The limit as x approaches a of f of x is L. All right. So if you've never seen this symbol before, and I suspect about half of you, maybe 2/3 of you haven't, okay? When you're going home and doing your homework tonight, You don't want to look at this and say LIM X arrow A F X equals L. If that's how you see it in your head, you're not going to get the concept down. You have to practice translating it into words first. Okay? So that's why I try to always give you the way you read the expression out loud. So I'll write it for you, but then I tell you how you're supposed to read it out loud too. Okay? So that's something that you want to practice doing. Okay, so let's look at this example here. Okay? This is the first example of an interesting limit that we're going to do. Okay? Before we get started, what is the domain of this function?
X is all real numbers except for 3.
Yeah, x is all real numbers except for 3. So in set builder notation, we say x such that x is any real number. X does not equal 3. Okay. Remember, what does this little symbol here mean? It looks like an E. I didn't draw very well. It looks sort of like that.
Is an element of.
Yeah, that's a symbol that means is an element of or belongs to. Okay. To be honest, if you eventually stop writing this x is an element of the real numbers, that's fine, because what type of calculus are we doing in this class? Real variable calculus. So, but I'm just trying to get you careful about this stuff. Okay? But specifically, x can be any number except for 3. If we wrote the domain in interval notation, it would go from it would go from minus infinity to 3, union to a 3 to infinity. That's the domain of this function, right? Now, why do we introduce this brand new topic of limits? Well, eventually it's going to get us, we're going to return to the question we had before of looking at slopes of tangent lines. That's why we need limits, to return to the question we answered yesterday. But before we even do that, limits have this interesting ability to describe how the function is behaving around a particular value. Okay? I am not asking you in this problem to tell me what f of 3 is. In fact, what is f of 3? What would we say if you saw this expression? You'd say f of 3 is what? Yeah, f of 3 is undefined. How come? Because literally it is not in the domain of the function, right? So f of 3 is undefined. Okay? But if I ask you what is the limit as x approaches 3 of f of x equal to, I am not asking you to plug 3 into the function. I'm asking you to describe how the function's behaving near the x value 3. And it might be that it's behaving very nicely around that value 3, in which case the limit will exist. Okay? It might be that it's behaving very erratically around that number 3, and the limit won't exist. Okay? So, what we'll do is, let's go ahead and plug some values that are near 3 into this function. Now, down below I've got a caveat on this, and but I'll say it right now, just to get get this out in the open right now today. This technique of building a table is not calculus. This technique of building a table and plugging in close numbers is not what you should be doing in any sections other than 2.1 and 2.2. Okay? As we go on, you cannot use this technique. This is just to give you an intuition as to where we're going. Okay? So a lot of people pay attention through the first 2 class periods, and then come to test, I see them with their calculators out. And I think, well, I wrote this test so you don't need a calculator. And they're plugging in tiny, tiny numbers into functions. Sometimes they get close to the right answer, usually not. Even if they get the right answer, it doesn't matter because it's not the technique that's appropriate. Okay? So we're going to use this technique here. We're only going to use it today. So we're going to take a number that is near 3. So our goal is to describe the limit as x approaches 3 of f of x. So let's take a number that's close to 3, like 2. So if I plug 2 into this function, well, let's see here. We have f of 2 is equal to 2 squared plus 2 times 2 minus 15 all over 2 minus 3. And let's see, that gives us 4 plus 4 is 8, right? Minus 15 is negative 7, all divided by a negative 1. So what do we get? We get 7. Okay? Well, that was a number that was somewhat close to 3. But we could bring in a number that's even closer to 3, like 2.5. And if I plug in 2.5, I get out 7.5. And if I plug in 2.9, I get out 7.9. And if I plug in 2.99, I get out 7.99. Okay? Now again, I'm building this table. This is not calculus. This is not working with limits. Okay? This is just giving you an intuition for how this is working. Now, the picture for what's going on here is I'm taking x values. I started with this x value right here at 2, and then I tried plugging in this value right here at 2.5, and then I plugged in 2.9, and then 2.99. I'm plugging in numbers that are getting closer and closer to what x value? 3. Did I ever plug in 3 itself? Well, heck no, I can't. This function is not defined there. But even if it was defined there, when you're doing a limit, you're not plugging in the number itself. Okay? You're examining the behavior around that limiting value. Okay? And we got various points out. When I plugged in a 2, I got out a 7, so that was that ordered pair right there. And when I plugged in 2.5, I got out 7.5. Okay? When I plugged in 2.9, I got out 7.9. Now let's come from the other direction. Notice that all of my choices for x values were on the left-hand side of 3. Okay? So let's pick some that are on the right-hand side of 3. I don't know, let's pick 4. If I plug 4 into this function, I would find that I get 9. If I plugged in 3.5 into this function, I find that I get 8.5. If I plugged in 3.1, I find that I get 8.1. And if I plug in 3.01, I would get 8.01. So here I'm plugging in values to the right of 3. And we're getting out ordered pairs that look like this. Okay? So what's happening? Well, it looks to me that if you thought of this as sort of a sequence of numbers coming from either direction, what does the sequence appear to be getting closer and closer to? Appears to be getting closer and closer to the number 8. Okay? So what would we say? We would say that the limit as x approaches 3 of f of x is equal to 8. The way I interpret this, and the way I think you should interpret this as well, as near x equals 3, the function gets, the function values, in fact, let me say that, the range values get closer, get arbitrarily close to 8. That is what's encapsulated by this sentence right here. That mathematical sentence encapsulates that idea, which is also sort of what we see in the table. Are we having a hard time reading my horrible writing? Type up all these nice math notes to avoid doing too much writing. My handwriting's horrible, so if you ever can't read it, please, I'm not offended if you say, what the heck does that say?
What does that bit mean?
Which one?
Near x equals 3, the range values give. What's that?
Arbitrarily. Yep, arbitrarily close to 8. Thank you. Now, we just ascertained the limit by looking at a table. Okay? Going forward in this class, starting from section 2.3 onwards, you may not ascertain a limit from a table. Okay? You'll have to justify it some other way. And I'm going to give you some explanations today as to why this table is a bad procedure for doing this. Okay? Let's see, Jody, would you mind closing the door? Thank you. Okay. Now, what you can do is, if I provide you a graph, and that's only if I provide you a graph, you can get the limit from a graph. Okay, I'll let you do that. Okay. So what does the graph of this function look like? Well, maybe you remember graphing this function in college algebra. The graph of this function looks something like, let's see here, 5. The graph of this function looks something like this. Okay. It's a little bit hard to see there. I don't like this whiteboard in here. It's really dark. There's the graph of this function. Okay, maybe you saw this in college algebra. What is it? Let's sort of a line with a hole in it, right? Where's the hole at?
3.
At the x value 3. In fact, if you could describe this hole as an ordered pair, which it's not a point, right? But if you want to describe it as an ordered pair, what's the location of this hole?
3, 8.
Yeah, it's the hole is located at, the place where nothing is at the ordered pair 3, 8. Okay. So the limit is a way to describe what's happening there. Okay. I can't plug a 3 into this function, but if I take the limit as x approaches 3, I can describe what the function is doing near there. And because the limit exists, then we can actually describe that behavior. All right. So C is, I think, an extremely important point for today. Okay? So notice that the answer to the question was not dependent upon finding f of 3. F of 3 might exist in a limit question. F of 3 might not exist in a limit question. It doesn't matter, because this is not a question of what is the range value when the domain value is 3. It is how is the graph behaving around, near 3. Okay? All right. So the above, this is really important. The above is merely a guess as to what this limit might be. And this guessing method will only be valid for this section. Okay? From here on out, you have to be able to do something other than, or from 2.3 on out, you'll have to be able to do something other than just guessing by looking at a table. Okay? So I'm trying to head that off at the pass, right? Because it just breaks my heart if on the first test you're just plugging in tiny numbers. You've missed the essence of what we're doing here. Okay? Even though that's what we're doing today. All right. So let me show you just to justify where we're going, and this is what we'll see in the next section. Let me do this actually the way we'll do it in future sections. Okay? So let's go ahead and find the limit as x approaches 3 of f of x. Okay? Well, what is the function f of x? I believe it was the function x squared. Was it minus 2x? Or is it plus 2x?
Plus 2x.
Plus 2x?
Minus 15.
Minus 15 all over x minus 3. Right? That was our function. Okay, so what did I do from this step to this step, folks?
Put the function there.
Yeah, I just replaced f of x with what its actual rule is, right? Okay. Now, the next thing I can do is, well, let's try this. Let's factor the numerator. Okay? The numerator factors to be x plus 5 times x minus 3 all over x minus 3. Okay? Well, what do we notice? What do we notice?
X minus 3 cancels out.
So we've got these two factors of x minus 3, one in the numerator, one in the denominator, right? So we can divide those out, and we're left with the limit as x approaches 3 of x plus 5. Okay? Now, this next part is going to take a little bit of work. Okay, so I'm just showing you this step. This is what you will do in future sections, but right now we don't really know why this works. Okay? The original function, what was the domain of the original function? Everything except for 3. Okay? Now, I've now reduced this down, and I've got a new function. Is this function the same as the original function?
No,
No, it's not. How come?
because it's a hole at 3.
Well, I mean, if I plug in a 4 into here, I'll get out 9. If I plug in a 4 into here, I'll get out 9. If I plug in a 7 into here, I'll get out 12. If I plug a 7 into here, I'll get out 12.
This one's defined at 3.
What's that?
This one's defined at 3.
Yeah, so even though these always return the same values for anything except for 3, this is not defined at 3, whereas this one is. So these are not the same function because they don't have the same domain. Even though they always return the same y values, If I plug in anything other than 3, they'll agree with each other. Okay? So this has a new domain. This has a new domain. But are we plugging 3 into this function? No. We're simply exploring the behavior near 3. Okay. All right. So this had a domain of all real numbers except for 3. This has a domain of what?
All real numbers.
All real numbers. Okay. And it turns out that if, let me just, again, I'm summarizing a very important point here, okay, that we need to spend a lot of time developing. But because this is now defined at the point where I'm trying to evaluate the limit, and this is what's called a continuous function, I can go ahead and apply what's called the direct substitution property. Okay? Which means that this will return the same thing as if we evaluated the function at that point. Okay? Which gives us 8. Okay? So here's a way of determining the limit, not with a table, not by looking at a graph, but by using algebraic properties. Okay? You should be able to follow all of the properties from here, from here to here. That should make sense. From here to here, that should make sense. From here to here, we've got some work to do before this is I mean, you might say, okay, I see what he's doing, but there's a lot of backstory to what allows me to be able to do that step, and I can only do a step like that in certain instances. Okay, so that's what we're kind of narrowing down our problem, right? The thing that we've got to do some work on. And so this is the part that's going to require some more work, but we've got a little ways before we can get there. Okay? All right. So why do we want to use limits at all? Okay? Well, because the limits describe the behavior around a point, not necessarily at the point itself. Not necessarily what the function's doing at the point itself. So here are 3 examples where we get different information in each case. Okay? So for this one here, let's look at the graph of f. Here I'm asking you to determine what is f of 4. We're just going to do this graphically here. What is f of 4? Yeah, f of 4 is -3. Okay? How do I do that? Well, I look at saying, when I plug in 4 into the function, what is the corresponding y value? The corresponding y value is -3. Okay? Now, this next step is a completely different step. I want to look at the behavior of the function near x equals 4. Okay? So I'm going to take x values, like maybe this x value right there. If I take that x value right there, that corresponds to this point right here on the graph, right? Which corresponds to what y value? This y value right there. Then if I take a different x value, like maybe this one right here, that corresponds to this point on the graph, which corresponds to that y value. And if we do one more, if I take, say, that x value right there, that would correspond to that point right there, which would correspond to that y value right there, as best I can draw on this tiny little picture. Okay? That was coming from one direction. Okay? What if we came from the other direction and we picked, I don't know, maybe this x value right there? This x value corresponds to that y value, right? Let me make that an arrow, not a point. That x value corresponds to that y value, to this point on the graph, which corresponds to that particular f of x value, right? And then we take another one. We bring that in closer, maybe right there. Okay? Well, that would be that y value. Okay? And then if we took one even closer, I don't know, maybe that one right there, that corresponds to that point, which corresponds to that y value. What are we seeing? As the x values get closer and closer to 4, the y values are getting closer and closer to what number? -3 again. So in this case, the functional value and the limit value agreed with each other. To be honest, one way of looking at it is, by evaluating the limit, we didn't really get any new information. We sort of knew that, I mean, we didn't get any new information. That's because this is a very well-behaved function, and I'm going to start using some vocabulary that we're going to define later. This is what's called a continuous function. When you have continuous functions, looking at the limits of continuous functions isn't very exciting. Limits are exciting when you're dealing with discontinuous functions. You learn more information when you're dealing with discontinuous functions. Okay? So let's look at this one here. Okay? Here I'm again asking you to find the y value when the x value is 4. What is it?
Undefined.
It's undefined in this case. Everyone okay with that? But what is the limit as x approaches 4? It is again -3 by the exact same argument we did on the first graph. So what's the difference here? Well, as far as the limit, there was no difference in the limit. Okay? But where we couldn't evaluate the function at 4, we can still describe how the function's behaving near 4. That's a handy skill. So even though this expression was undefined, g of 4 is undefined, we can still say that the y values near 4 get closer and closer to -3. Okay? So I'd like everyone to we're going to practice reading this. Literally, we read this as the limit as x approaches 4 of g of x is -3. That was pretty bad. Let's do it again. The limit as x approaches 4 of g of x is -3. Okay, I'd like to now say this a different way. As the domain values get close to 4, the range values get close to -3. Altogether, as the domain values get close to 4, the range values get close to -3. Okay? You need to be able to spin both these interpretations of this little mathematical sentence, right? Math is powerful because somebody much smarter than us came along and came up with concise and precise notation for describing complicated ideas. Okay? That's why it's so powerful, because you can do a lot with this precise notation. But if you can't unpack that precise notation, then it's not helpful to you. So you need to learn to unpack it the way I just did. Okay? Okay, so finish out this next one, check with your neighbor.
Yeah.
Is this,
Yeah.
does this play a factor though?
So this one,
Are you gonna pick up the quiz?
discontinuous.
If you're ready to turn it in, yes. If you want to wait until you finish during the break, I'll take it then.
We may have a little
At the value
Okay.
of x is 4, it is at least defined, but
Right, but it's
5.
not.
From here it is. 'Cause that's it.
Exactly.
Okay, so what is h of 4 in this case? Beats me. That looks like 5. Is that a 5? I can't read it. It's so tiny. Okay, that's a 5. Okay, and what is the limit as h approaches, or x approaches 4?
-3.
It's the same one. Okay, so in this case, notice that the function value exists, the limit value exists, and they agreed. That's nice. That's actually one of the ideal cases. Okay, that's what we're always, life works well when this is the case. Okay? Here, the functional value is undefined, and the limit exists. Here, both of them existed. Both of them exist. The functional value exists, the limit exists, but they don't agree with each other. Okay? There's two other cases that I've not put up here. One where the functional value exists, but the limit doesn't, and one where neither of them exists. Okay? And we'll look at that in some other cases as we go. This isn't all possibilities of what could happen. Okay? All right. So here's a nice little statement, number 4. I'll let you read through it. It's basically just summarizing what we just said. Again, 4 and 5 basically summarize what we just said. All right. So let's look at this function right here. Okay? Here's a nice, interesting function. I would recommend putting this function on a flashcard. It's just, some of these initial cases that you're sort of you're not used to dealing with, you should put on flashcards just so you have these facts as you need them. So here's the function, the sine of x divided by x. Okay? What's the domain of the sine function? Yeah.
From 0 to infinity.
Yeah. The domain of the sine function is all real numbers, right?
It's the range.
Yeah, the range goes from -1 to 1, right? So the domain of the sine function is all real numbers, right? Okay, what's the domain of the function just x? It's all all real numbers as well, right? The identity function's domain is all real numbers. But now I'm looking at the quotient of the two,
And it can't be 0.
and you cannot divide by 0, right? So the denominator of this expression can't be 0. So this function is not defined at 0, so f of 0 is undefined, right? Everyone okay with that? Okay. Now, even though the function's undefined at 0, it still might behave nicely around 0. And in this case, it does. Okay. You shouldn't think that it has to behave nicely around 0. And I'll give you an example of one that does not behave nicely around 0. Okay. So here we'll just look at I've done the work. There's the graph of this problem. Here's the table, right? Okay. And how do we then go ahead and determine this? We look at what would we say the limit is? We'd say the limit as x approaches 0 of the sine of x over x is equal to what? 1. Okay. Now, again, this is still a guess method. Okay. Unfortunately, we won't actually prove this limit until chapter 3. Okay. In chapter 3, we'll prove this limit if we have time. If not, we'll prove it for sure in chapter 4. This one's a lot harder to show that this is in fact the limit. So from here on out, you can take this one on faith. You can use this fact as you wish. Okay? That this particular limit comes out to be 1. So I would put that on a flashcard or something like that, so that if you see this limit, you know it without having to do any work. Okay? By the way, how many of you had a physics class before? A couple physics classes. Okay? I don't remember exactly the application. I think you do it a lot with pendulums in physics classes, where the function that you're working with has a sine of x expression in it, and the instructor says, oh, we can actually just replace that sine of x function with just an x. The fact that this limit is 1 is related to that idea of saying, in fact, here's one way to look at it. If I graph the line y equals x right here, there's the line y equals x. Notice near 0, those two functions behave similar to one another. So near 0, it's okay to sometimes use x as an approximation for sine of x. Anyway, so maybe how many of you have seen that before in a physics class? All right. Now, these next few examples are justifications as to why we are not always going to use this table technique. Okay, I'm going to show you several instances in which this table guessing technique breaks down. Okay. So the first way this could go wrong is choosing. I'm going to use the phrase choosing an incorrect path towards the limit. Okay. So here I've got this function right here. The limit is x is approaching 0 of the sine of pi over x. Okay. Well, if I pick x to be 1. But that's not quite to 0, but we'll get closer and closer to 0. If I pick x to be 1, okay, then I'd have the sine of pi. What's the sine of pi? Sine of pi is, right, that's the sine of 180 degrees. That's 0. Okay? So when x is 1, we get out a 0. Okay? What about when x is 1/3? Well, that would be the sine of pi divided by 1/3. That's the sine of 3 pi. What is the sine of 3 pi?
0.
It is also 0. So when x is 1/3, it's also 0. What about when x is 1/4? Same argument. What about when x is 0.1? Well, that would be sine of pi divided by 0.1. That's the sine of 10 pi. What's the sine of 10 pi? 0. It seems to me that for these values, as I'm picking them, as the values are getting closer and closer to 0, what are the y values getting closer and closer to as well?
0.
Also 0, right? It appears that the limit as x approaches 0 of the sine of pi over x is 0. That's what it looks like, right? Based on these numbers that we picked. But this is where this guess and test method is not good enough. Okay? Because in fact, the graph of this function, let me get it right here. Let's see here, pick something just large. Pi will be negative. In fact, the graph of this function looks something like this. Let's see if I can draw it. came from the other way, negative pi, so left negative pi. Think. That's what the graph of that function looks like. As we get closer and closer to 0, what are the y values getting closer and closer to? What do they seem to be approaching? What do they seem to be congregating around? What y value? This y value right here? This y value right here? This y value right here, right here, right here? Which one do they seem to be getting closer and closer to? None of them. This function oscillates exceedingly rapidly as we get closer and closer to 0. The closer we get to 0, the more rapidly it oscillates. Okay? This function behaves too erratically. This is not a function you've probably seen before. This is a function that behaves too erratically near 0 for us to describe what it's doing near 0. So in fact, we would say that this limit does not exist. So this is almost the worst case scenario, right? I mean, here's an instance where the limit did not exist. Okay? Certainly 0 is not in the domain. Does everyone agree 0 is not in the domain of this function? Because we'd have the sign of pi over 0. I can't divide pi by 0. That's undefined. So certainly 0 is not in the domain. But not only that, but around 0, the function's not behaving nicely. The limit doesn't exist. Okay? It's oscillating too rapidly. So this is an example of the first example I've shown you where the limit itself does not exist. The functional value didn't exist, we knew that, but neither did the limit. Okay? However, if I tried this guess and test method, I just so happened to pick all of the points where it was crossing the x-axis. So I chose an incorrect path in, and it made me believe the limit was something other than what it really was. So that's the first way this guess and test method can break down. Okay? Any questions on that? Okay. The next one is not approaching close enough. Okay. That's another way this method could break down. Okay. Let's look at this table of values right here for this particular function, the function x cubed plus the cosine of 5x over 10,000. Let's say we picked 1. Okay, there's the y value I've calculated for you. Let's say we picked 0.05. There's the y value I've calculated for you. What do the y values appear to be getting closer and closer to? They just keep getting smaller and smaller, right? Right? So you might incorrectly guess that the limit as x approaches 0, we'll just call it f of x, is equal to 0. That's what it appears, right? They just keep getting smaller. But we didn't do what? We didn't approach close enough. Let's keep going. Wait a minute. This isn't approaching 0. Okay. And in fact, it turns out that this limit is, what is that? That's 1 over, is that 10,000? Hundreds, thousands, yeah, 1 over 10,000. Oh, I should have done that, yeah, obviously. 1 over 10,000. Okay. Which is a number that's close to 0, but isn't 0. Okay. So again, this whole sequence of examples is to give you warning and justification why you cannot use this table method. And if you use a table method on a test, if you start plugging in tiny numbers into your calculator to guess at what the limit is, I can't give you credit for it because it's not a valid method. Okay. The next one is, and I'm not going to show you an example of this, using a machine to estimate values where round-off error produces erroneous results. If I have time during the break, I might pull up an example of that happening. The way computers calculate, the way computers do operations, you can often experience a round-off error which gives you a completely wrong result. Okay? And so I've got an example of that, but if you have a chance, I'll bring it up during the break. Okay. How are we doing? Pretty good. All right, so the next thing I want to introduce is the notion of left and right hand limits, okay? So, this definition looks very similar to our definition of the limit, what I'm going to sometimes call the limit proper, the limit definition that I gave before. So for a function defined on some open interval of the form a comma c, okay, if as x approaches c from the left, the range values approach some value L, then we're going to write the limit as x approaches c from the left of f of x is equal to L. This is the same idea as before. We're saying as the x values get closer and closer to some number, in this case I'm calling it c, if as x gets closer and closer to c, the y values get closer and closer to L, then we'll make this limit statement. What's the difference? We are only approaching c from one direction. What direction? From the left. Okay. How do I denote that we're approaching from the left? I put a little minus sign up there. That means we're coming from the left. Now, this is very important, folks. The direction of approach is from the left. The value that we're approaching then will be to the right of where we're approaching from. Okay? Left and right is always a matter of relative position, right? So I'm saying the direction of approach is from the left. Okay? So a lot of times people get those confused. They switch them up. Okay? The direction of approach is coming from the left. So this is read, the limit as x approaches c from the left of f of x is L. In this case, we would call L the left-hand limit of this function. Okay? So let's go ahead and denote that graphically. Okay? Here's the value c that we're approaching. Okay? So if we take x values, let's say we take this x value right here. That corresponds to that point on the graph up here, which corresponds to this y value right here. Now let's say we pick another x value. Let's go a little bit closer. Let's pick this x value right here. Okay. That corresponds to this point on the graph right here, right? Which corresponds to this y value right here. Now let's go closer. Let's go to here. Okay. That gives us this point right here, which gives us this y value right here. And as we get even closer, what does it seem that our y values are approaching? They're getting closer and closer to whom? To L. Okay. Now, we only picked what type of x values? X values that were where? X values that were to the left of c. So how do we denote this picture? We would write the limit as x approaches c from the left of f of x is equal to L. So let's practice reading this aloud. This says the limit as x approaches c from the left of f of x is L. As the as the domain values get closer to c from the left, the y values get closer to L. Okay? So in these problems, I think it's very important to always be thinking of domain and range. Okay? As the domain values get closer to c, but specifically coming from the left of c, the y values get closer to L. All right. So what do you think I'm defining here? Yeah, we're defining the right-hand limit. Okay? And the only difference in the definition is we're saying as x approaches c from the right, then what do you think we write? The limit as x approaches c, how will I denote this? From the right. We'll put a little plus sign. That plus sign is like a, both the plus sign and minus sign there are in like a superscript, a power position, right? Of f of x is equal to L. So this is read, the limit as x approaches c from the right. So the picture that goes with this is I'm going to take x values to the right of c, one's off the graph, but that's okay. I guess we got it, yeah. What do we see here? We see as the x values, so as the x values approach C from the right, what are the y values doing? What are the y values doing?
Approaching L.
They're approaching L. All right. So here's an example of a function that's called the Heaviside Function. To be honest, there's many different definitions of the Heaviside Function. I picked one that was just a little more interesting for the graph's purpose. Okay, this is a really important function in physics. It sort of models the flipping of a switch. So before the switch is flipped, what's the current? 0. And after the after the switch is flipped, you've got current. Okay? So this is a function that will model that. Let's graph this. This function looks something like this right here. So that's the Heaviside function. Okay? So before the switch is flipped, which happens at time t equals 0, there's nothing. After the switch is flipped, there's something. Okay? Now, this particular Heaviside function, this is not how all books define it, but I like this definition just because it makes me put a point there at 0 as well. At the ordered pair what? What's that ordered pair there? 0, comma, half, right? Okay. All right, so let's make some statements. What is h of 0? Actually, we just made that statement. What is h of 0? H of 0 equals a half. Okay. What is the left-hand limit as x approaches 0 from the left? What do we get? 0, right? Okay. Let's write that in full limit notation. The limit as x approaches 0 from the left of h of x. We're using x? No, we're using t. Of h of t. Sorry, folks, I should be using what here as my domain variable? T, because this kind of fits in the context of time. Okay. The limit as t approaches 0 from the left of h of t is what?
0.
0. And what about when we approach from the right? It's 1. Right? We'd say the limit as t approaches 0 from the right of h of t is equal to 1. Can we all see that okay? Any questions on that? Okay. Okay. Based on what we just saw about left and right hand limits, we can now give a new definition for the limit. Okay? Sometimes folks, when I say the limit, I mean the limit as we just defined it on the first page. But sometimes to help distinguish between left and right limits versus the limit, I will call it the limit proper. Does that make sense? Okay. So we can now give a new definition of the limit proper. Okay. So we say that the limit as x approaches a of f of x is equal to L if the limit as x approaches a from the right of f of x equals L, and the limit as x approaches a from the left of f of x is equal to L. So another way of defining the limit proper is to say if the left and right hand limits agree with one another, then whatever value they are will be the limit proper. So we can fill in the blanks here. We would say that the limit exists if and only if the left and right hand limits exist and they are the same. How are we doing, folks? All right. The book doesn't talk about this concept at this point. It waits until section 2.4. But I want to go ahead and introduce it now just so it's starting to simmer on the back burner, because this is one of the more difficult topics that we talk about. Okay? Let's look at the graph of this function right here. Okay? This is the graph of 1 over x squared. It looks like this. Okay? Make sure you're able to graph that on your own. If somebody said, what does the graph of 1 over x squared look like? You should be able to graph it on your own. Well, we'd like to describe the behavior near x equals 0. Okay? The limit is not going to exist, right? Let's make sure that makes sense. If I pick, say, this x value right here, that will correspond to this point right here, which corresponds to that y value, right? And then if I bring it in even closer to 0, that would correspond to this y value way the heck up here. As I bring it even closer to 0, it gets even higher, right? What fixed y number are we approaching? We're not approaching a fixed y number, right? So the limit doesn't exist. This is a very subtle point. The limit doesn't exist. But unlike that crazy sine function that we looked at, we still want to say something about what the function's doing here. Okay? So we're going to say that the limit as x approaches 0 of f of x, we're going to say that it is infinity. Now, this is extremely important. I'm not saying that the limit exists. Okay? We're just using sort of the same notation that we did before. This just says as x approaches 0, f of x gets arbitrarily large. So this sentence right here, this mathematical sentence, gets translated this way. That's a tough concept. We'll spend some more time on that as we go through. Okay? Any questions on that? Getting some dull looks. I don't know. Feeling overwhelmed? Give me thumbs up, thumbs down as far as how we're doing. Thumbs up is good. Thumbs down is bad. Thumb sideways is, okay? All right. Okay, so that's what we just said. Let f be defined as some open interval around a itself. Then if the values of f become arbitrarily large, as x approaches a, then we write the limit as x approaches a of f of x is equal to infinity. Now I'm not claiming the limit exists. I'm not claiming that our y values are approaching some fixed y, some number L, right? But I'm still describing the behavior of the graph near that value. If the f of x values become arbitrarily I'm going to write this phrase here, large negative, meaning they become negative numbers getting more and more negative. Okay? Then we write the limit as x approaches a of f of x is equal to negative infinity. Okay? And I could have done this for left and right hand limits as well. Okay, so most of the limit stuff I described applies to both left and right hand limits as well as the limit proper. Okay, so let's just say why we want to be able to describe things this way. If the value of the limit, meaning the limit proper, or the right hand limit, or the left hand limit, is either written as infinity or minus infinity, meaning it becomes arbitrarily large in the positive sense or arbitrarily large in the negative sense, okay, then we say that f has a vertical asymptote at x equals a. Okay, so that is the definition of a vertical asymptote. So I know that graphically, you guys have experienced vertical asymptotes before. Ooh, that got shifted off a little bit. graphically, you guys have experienced vertical asymptotes before. This function, 1 over x squared, has a vertical asymptote at x equals 0. The justification for that is that one of its limits at 0, either the left or the right, or the limit proper, came out to be infinity or minus infinity. When that happens, you've got a vertical asymptote. Okay. All right, we'll skip F for right now. So let's see what page we're on. We'll do this one. Yeah, we'll do this one real quick. So I'd like you to, in your groups, go ahead and answer. Go ahead and answer both 13 and 14. Okay. Check your answers. Get your stories straight. If I come around and you guys have different answers, I'm going to pick on you. Okay. So make sure you're putting the same thing down.
How'd you guys get one more for the second one?
Yeah, like this, yeah. It's cheaper in Colorado, so. But I mean, not necessarily.
Okay, folks, let's go ahead and get back to it. If you would, go ahead and give number 15 a shot. Work through number 15. You see that this limit notation does, in fact, further help us to describe what's happening around a particular point on the graph. It's just knowing the y value, even if the function's defined there, isn't enough to say what's going on. Let's see here. We want f of 2. Well, f of 2 is undefined. I don't know why I put equals. It should just be undefined. Undefined. Whereas the limit as x approaches 2, help me out, I think that's 2. It's a little hard to read this axis. So 2? Yep. What is the limit as x approaches 5 from the right? Well, that appears to be, looks like 3. As we approach 5 from the right, it appears to be 3. All right, so here's one that we don't get a lot of examples of. What's the limit as x approaches 5 from the left? What do you say?
Does not exist.
That's some for does not exist. Any other guesses? Undefined. Other guesses? Yeah, so for those of you who say does not exist, why is that?
The range
It's
is
too erratic.
going.
Yeah. So what range value are we approaching? Are we approaching that range value? No, because as we go even closer to 5 from the left, we'll eventually go below it or above it. Right? Pick any range value that you think the limit should be, and you eventually go above it or below it. So in this case, we would say not undefined, but close. We would say does not exist. Okay. All right. I think that's all I want to do. Let's go ahead and do number 18A. Okay. So this is just some extra practice. I do. You guys have all the tools you need to finish these problems out. The rest of the examples in these notes. So go ahead and try to do that on your own time. Let me know if you have any questions. But let's have you guys do 18A as a group, okay, in your groups. Try to come up with this. Okay, folks, I want to talk about this problem altogether. Okay, this will show up on a question like this will show up on your attendance quiz next time. So you'll know one of these is coming. Okay. The first thing I would say is let me say two things about these types of problems. The first thing is if you're completely lost, just put a guess down and then check it, right? So. And that probably involves then using pencil so you can erase as you need to. But put a guess down so you can check it, and then adjust as necessary. That's how I tackle these problems. I don't just look at this and say, aha, I can see it all together and graph it. Okay? So put something down, check it, and fix it. The next thing is make sure that when people get this problem wrong, it breaks my heart if they get it wrong because they don't even draw a function. A function has to do what? Remember the vertical line test? You can't have two ordered pairs for the same x value. So absolutely make sure that you pass the vertical line test. Okay? So let's see what we can do here. Here we're told that the behavior around the y value 1, around the x value 0 is the y value, it has range values of 1. So we know that something like this is happening. We know something like that has to be happening. It doesn't matter whether your line's coming up like this or going down like this, right? But this limit statement tells us that much information. Okay? Let's go ahead and also put in this fact. This is an ordered pair, right? That's a domain range ordered pair. So we know when x is 0, the y value needs to be -1. Do I still have a function? Yes, this still passes the vertical line test. Okay? So could I fill in this point here? No, this point has to be open. Okay? Now let's look at what's going on with round 3. Well, we're told as we approach 3 from the left, let's see, 1, 2, 3. As we approach 3 from the left, we should be near the y value -2. So I should have something like this. All right? As I'm approaching 3 from the left, what are my y values doing? They're getting closer and closer to -2. As we approach 3 from the right, our y values need to be getting, that should be a little bit higher. I didn't make my scale big enough. Should be looking something like that, right? Okay. And when we plug in 3 into the function, it needs to spit out a 1. So that's that point right there. Does this still pass the vertical line test? Is it still a function? Yes, so please, whenever you draw this, make sure, first off, that it's a function. Okay? Because if you don't make a function, there's no way, I like to try to find ways to give people partial credit. I can't really do partial credit if it's not a function, because I don't even know where to begin trying to, assign points. All right, so what do we got? Well, we got something that looks like a biology class, but we can go ahead and finish, connect this however you want, right? I just said to come up with an example that met all these criteria, and sort of regardless what you do, you basically have to have a function that looks like this around these interesting points. But then you can sort of finish connecting the dots however you want. It doesn't matter. Here we go. Okay. So your graph may not look the same as mine, but does it look the same at these points of interest? Around 3, does it look the same as mine? And around 0, does it look the same as mine? That's what you have to have. Okay. All right. So I would encourage you to do letter B here. I think it's a good problem to work for next time. And C as well. These are all nice, interesting graphs. So go ahead and work them for next time. What I'd like to do now, though, is we're going to move on to the next section.